the composite load. What happens when the load is resistive inductive or resistive capacitive or resistive inductive capacitive? And I was kind of talking to myself. No, actually, there were three of you on the lecture. And I said, oh my God, the last one I don't want to do because it's so long. And this formula is like, ah. That being said, I have it here. So what I'm going to do, since I don't want to spend a lot of time, this is just algebra. And we're not here to talk about algebra. So what I'm going to do, I'm going to write the beginning of the process and the end formulas, and I will give you a copy of every step so that you can review. It's math. So I don't want to spend a lot of time on that. So with that said, let's look at instantaneous power for RLC load, P of T. And basically, once again, it can be a circuit that looks like this. I'm going to pull three elements, and this can be L or C. Remember, we talked about depending on the size of the capacitor, one can override the other. Capacitor being negative and inductor being positive. So in this case, the formula, so V of T, of course, and I of T is equal to V of T equals to V max cosine omega T plus some angle P V. And I of T is equal to I max cosine omega T plus Phi. Okay, so those are the general equations for the source, the current being supplied by the source to the load, right? And again, this is RLC load. P of T is equal to V of T times I of T. So it's just the product of the voltage and current. So then we say that P of T is equal to V max cosine omega T plus P voltage times I max cosine omega T plus I for the angle of the current. If we start expanding this equation, we can say V max I max cosine omega T plus some angle P voltage times the cosine omega T P of the current. So on the previous one, in many cases, we were able to use we had control of the angle. We knew what the angles really were, right? In this case, we don't know. So we leave them separate as Pi and Pv. So if you expand this equation, let me see, where should I take off? I'm not gonna, like I said, I'll give you all the steps, but I'm gonna jump to this P of T, and I'm gonna put this 3 dots so that you know that there is more. V RMS, I RMS, cosine of phi V minus Phi, plus VRMS IRMS cosine 2 omega T plus 2 VV times the cosine of phi of the voltage and phi current, plus there is a third term right here, VRMS IRMS sine 2 omega T plus 2 phi V times sine phi V minus Phi. So again, I skip a bunch of stuff. I'll give it to you, but I want to get to this part of the equation when I have three components: this component, and this component. You can see that this component, there is an angle here that is constant once you define it. Then there is, in these terms, there is a function of time, there is a function of time, but there is also two components that are constant once you define the angle, of course. So with that, with this equation, this is one equation. I'm gonna do this. I'm gonna say let I R equals I R M S, and I X equals also I R M S. So the RMS value of the current of the resistor, I'm sorry, the current through a resistor or the resistive part magnitude, and the current magnitude of the reactance, and it can be capacitance or inductance depending. And I'm gonna say that cosine PV minus PI, and second is sine PV minus PI. So if I use this, I'm gonna say that P of T is equal to, when I use this VRMS, I'm just gonna call it VIR plus V IR also, cosine 2 omega T plus 2 V plus V RMS IX IX sine of 2 omega T plus 2 V, and then that's one. Let me see. Yeah, and then last but not least, P of T is equal to V R M S I R times 1 plus cosine 2 omega T plus 2 V. I'm gonna close this. I'm gonna open this brackets. Plus V R M S I X sine 2 omega T plus 2 V. All right, so again, I'll give you the whole variation. I just kind of wanted to get to this point. I'm going to call this part of the equation, right here, is my P R of T. Ooh, this is not a nice color. This part of the equation. If you go back to what we did before, this is P R of T, which we already derived. Meaning this is the instantaneous power consumed by the resistor. And this right here happens to be Px of T. So this part right here is the instantaneous power consumed by either the capacitor or the inductor. So this is the resistive and the inductive piece. Once again, this is a composite load, so you need both values. So here, with that said, I can then, or my goal, or our goal is really, how do we then capture out of this, out of the sinusoid, I mean the instantaneous power of any load, in this case being composite load, is a sinusoid, right? So if you plot this and you have the values, you're gonna get a sinusoid, and the sinusoid is gonna be either up or down from the x-axis. What do I mean by that? So if I was to plot this, maybe use a different color. And we're gonna do this in MATLAB just so that it's nice and clear. I'm just going to use this as a reference. When I say the voltage, I'm going to use voltage for now. And then I'm going to use the instantaneous power. What I'm going to do is this. Oops, sorry about that. Do it again. That's what I like my no, not nice enough. Hold on 1 second. Wait. Okay. I'm just gonna remember the voltage. One full period of the voltage is 1/2 period. I'm sorry, of the voltage is 1 full period of the instantaneous power. And yes, remember, right, when we did the resistor, we said, oh, the resistor looks like this, right? And I said, oh, you have all these positive areas, so that is what is being consumed by the resistor. If you have a capacitor, we said, oh, we have something that looks like this, right? And if you have, I'm sorry, an inductor, if you have a capacitor, then you have kind of the same thing, but in reverse, 180 degrees from each other. But we said for the inductor, after one period, the total area under that curve is 0. Remember I said that? And I said, oh, that's the reason why inductors, they don't consume any power. What they do is they borrow it from the source and they put it back to the source. Borrow, put it back at 120 hertz. Okay? The capacitor is just the opposite. I said, but at the end of one cycle, the net energy consumed by the load in the form of reactive power is nothing. It's none. Now, when you have a resistor and a inductor, as an example, you're going to have depending on the size of the resistor, you're going to have an area, positive, and then you're going to have this little negative areas for one cycle. That area right here, that is on the top, is what is consumed by the resistor. And these little areas at the bottom, on the negative side, is what's consumed by the inductor. So the way you can think of it, oh, if I take this area right here, and I somehow subtract it from here, right? This is positive, this is negative. I take it out, I still have some remaining energy consumed by the resistor. But it's not symmetrical to the x-axis. There is a shift, and that shift is based on the size of the resistance on the circuit. Okay? And like I said, we'll do this in MATLAB so that you can visualize it. But this is really telling us is, oh, and this is when I was saying, if you think of a circuit, and I think I mentioned this, and I'm going to say that the wire is a pipe, and here's my load, resistive, inductive. There is going to be, say, there is going to be energy flowing through this to serve that resistive part of your load at your home. But then there is also going to be some reactive energy to serve the inductive part of your load at your home. And I said, this can be your lighting. I'm going to use lighting. If you have an electric heater, actually, that is what it is, a resistor. And this can be, I don't know, motors that you have in your homes, your washer, your dryer, your air conditioner is basically a reactor. But this is telling us is that all that area there has to go, that power has to flow through this wire. Okay, some of it will get consumed by the resistor and never get back. Some of it will go back, but you still need the pipe. Whether you leave the energy there, or you're cycling the energy, you still need a pipe to carry it, but to carry the energy. Do I make sense, everybody? All right, and we'll do it some other way so that, if it didn't make sense here, it will make sense at some point. And that's the behavior now of a load that is what we call composite. But the other thing that we said was, yeah, but how do I measure that? I mean, how do I use this equation right here to measure the power that is going to be flowing here? How do I get that average? I'm going to call average power flowing through the line if it's always moving. I mean, of course, nowadays you have the ability to do that, right? Mathematically, you can do it. But if you want to make this equation here that we're looking at, the instantaneous power equation, a little easier to deal with, just like when we're talking about instantaneous or time domain voltages and phasor voltages, there's information inside the waveform that can help us determine the amount of energy that is required. Okay, so with that said, just like the instantaneous, just like the time domain signals, voltage and current, there is a case in these equations, a piece that doesn't really move. It's not subject to time. And if you're able to capture that, then we have the ability to measure power. And that's what we then call, the average power. And that's what you guys now talk about when you talk about, the amount of power that you consume at home is what we call average power. So average power, out of that equation, by the way, power is equal to P equals V RMS times IR. And I define IR there. So, I said that IR is equal to IRMS times the cosine of the angle of the voltage minus the angle of the current. And it's always like this. It's not the current minus the voltage. It's always voltage minus current to get the right angle. Oh, okay. So somehow I put that in there. I made a substitution. I created this variable IR. So then I can rewrite P equal VRMS, magnitude, by the way, not the phasor. This is magnitude too. This is a magnitude because this is an angle, right? Once you define the angle between the voltage and the current, this is constant. Times IRMS cosine V minus PI. Oh, okay. And by the way, I'm going to put it here. We call that theta. V minus PI. So the angle, phase angle. This is called the phase angle or theta. So if I know once again the voltage phase and the current phase, that being theta, the cosine of that times these two magnitudes gives me P, or what we call billion power, and we call that watts. But if you look at this equation and look at the units of that equation, we call it watts, but it's still amps times volts, right? Amps times volts. This is constant. So, but we happen to call that watts. Okay? So if you go here, it's really out of this equation right here. VRMS, IRMS, O is that shift that we were talking about in that equation for the purely resistive load. So I'm just taking the piece that is not time dependent because I don't care about that. Okay? Oh, same here. Is this is moving with respect to time. I'm only interested in this in itself. The average power can tell me what the load is if I know the load voltage and current. So that's that. Now Q magnitude, we'll change it to the right units of the right value. Q is equal to VRMS magnitude times IX, and I define IX. I don't know why I left this big space right here. This is what I substituted with. Oh, okay. So IX is equal to Q VRMS magnitude times IRMS magnitude, and IX is the sine of VV minus VI, or better yet, just for sake of completeness, this is the imaginary part. JQ is equal to VRMS J, IRMS, both magnitudes, sine of theta. And this is the units for the imaginary power is volt ampere reactive of bars. We use plural because bars. So watts for the real power or the real part of the apparent power, and Q or bars for the imaginary part of the apparent power. And we'll talk about that in a second. And we happen to call it bars. But the root units of it is ounce times volts. Okay? So the product of those two, whether it's real power or imaginary power or reactive power, regardless of what we call it, still the product of your voltage and your current. And with this, now you don't have to you don't longer have to worry about this time variable. Okay, so basically you're extracting the average value, and that's the average. The way you can think of it is that's the average energy encased on that waveform, real and reactive. That's basically what we're able to do with this. So this formula and this formula. Okay. Then there's third. So this is what's called like real power. And I'm going to write imaginary or reactive power, the same thing. Okay? All right, so with that, I can also derive or define a third measurement for power, which is what we call apparent or complex power. And the apparent power, I'm going to go here. Your apparent power is equal to, do I have it here? Did I miss some pages? Hold on one second, everybody. I did, but that's fine. I'll remember. So the last one is what we call apparent. It's two pieces, I think. Apparent power, or also known as complex power. And the complex power is the combination of these two. So S, and it's defined by the letter S, is equal to P plus GQ. If it's an inductive load, this is positive. If it's a capacitive load, this is negative. So this can be plus or minus, but let's leave it as plus right now. And the units for this whole thing, not just one, is volt amperes. Okay, so this is watts, this is bars, and the combination of the two is what we call volt volt amperes.
Oh, sorry, what does bars mean?
Volt ampere reactive.
Oh, okay.
Volt ampere reactive and volt amperes. Now, what are the units of those? Volts times amps. This one is easy. It tells you right there. Okay? So that's one way. You can also use the following formula to find the apparent power. S is equal to V phasor. Phasor. These are magnitudes. This is real. This is imaginary. In this case, if you know the phasor, the voltage phasor, you multiply this by the current phasor conjugate. Okay, you get the same thing, volt ampere. So that's just another way, depending what piece of information you have. And we'll do a few examples. So again, in summary, we have real power, imaginary or reactive power, and complex or apparent power. Okay, and all three of those give you information about the system and what the system is doing. Remember I said I don't like analogies. Remember I said I don't like, but this one I learned to like it. I don't like it at the beginning, but I learned to like. Yes, sir.
What is the asterisk for?
Conjugate. Remember when you have, if I have, I'm going to say a unit phasor of 1 magnitude 20, U conjugate is equal 1 angle minus 20. You remember that? You remember the conjugate? It's just telling me that, hey, if I have an angle that is positive, magnitude doesn't change. What it changes is the sign of the angle. So if I have t equals to 1 angle minus 30, t conjugate is equal to 1 angle 30. You guys remember that kind of sort of? This is the conjugate of the current. And why? If you don't put the conjugate, meaning if you don't negate the angle, you're going to get the wrong answer. Because really what we're after is the angle between the voltage and the current. Otherwise, you get it wrong. All right, so back to my story. And as I said, I'm going to say this. And then we're going to put this into a real life example. I'm going to say that this is I don't know, mug. Stain, Germans call stain, right? The thing that you used to drink. By the way, I am not promoting drinking. I drink, but that doesn't mean that I'm promoting it. And if and I don't want you to go test it if you don't drink. You don't have to test it. But I'm gonna say this, okay? So if you take a beer mug and you say, all right, I'm gonna fill it. I'm gonna fill it up. And then you fill it up to this point. Germans do that, right? They have, if you get a German beer glass, they have a line. And what it's telling you is the liquid better be there. That's what you're paying for. That's what that line is. So I'm going to say that this line right here is, under the line is the real power. This is the liquid. This is real power. The analogy is that that's what makes me happy. At least I drink when I'm happy. I don't drink when I'm sad. That's what makes me happy. That does the work for me, to my brain, whatever. Okay, I'm happy. It's doing something for me. What's left here is foam. Foam. This is Q.
And the whole thing is apparent.
Yes. And the whole thing here is S. Okay? So, foam. And you're going to say, yeah, as a matter of fact, that's the German law, beer law, that they should give you the liquid up to that point. Above that, it can be foam. You're paying for what is on that line. The foam, if they just give you foam and it's not going to do anything. All it's going to do is air. It's air, right? Nothing. It doesn't make you happy. It won't make me happy. It's foam. But the foam tells you a lot about beer, by the way. If you get a beer that is not new, that is it's been sitting there for a while, the foam doesn't, it's not there, right? It's not fresh. So the foam tells you the freshness of it. So there is a use for the foam. It's telling you something. On the beer, it's telling you, yeah, this is good beer. If it doesn't have foam, forget it. I'm not paying for it. So that's the way you can think of real power. Real power, that's work. You move something, whether it's heat, whether it's movement from a machine, that's what is doing it. The foam, you can say, yeah, but you do the foam. Because what the foam is doing for you, that the foam is responsible for the magnetizing part of the circuit. So when you have conductors, when you have transformer windings, when you have motor windings, the winding, the magnetic field that is produced is the one that is asking you for the bars. So they might not do work for you, but without it, you cannot do anything. Without the Q or the imaginary power, your system won't work because you do need that energy, right? The challenge is that once again, you take it and then you give it back to the source. You take it, you give it back to the source. And S is the size. Like he said, the S is the total thing. So I can say, all right, if I have a mug, I can decide, I can put half of liquid or P and half of Q. Still, this is the combination of the two. Okay? And it's what we call the MVA. All right, so with that being said, I'm going to be moving into a real life example for us electrical engineers. Now that you kind of have an idea of what this does and what this does for you. And we get into more details about this and this, by the way, as we progress in the course. I'm going to talk about another box here called transformer. And you can think of the transformer just like that mug. The transformer size, and that's when you talk about transformers, when we'll talk about transformers, we're going to say, what is the transformer MVA? What is the capacity? What is the room that transformer has? That's S. That's the MVA of transformer. Now it's up to you. It's up to you, based on the load that you're hanging on that transformer, how much P and how much Q, or Q and P, are you using out of that transformer? So if you want your transformer to be as efficient as possible, you want more P than Q. You want to minimize the amount of Q that the transformer can transfer one side to the other. By the way, the transformer itself absorbs bars. So not only transfer bars from one side of the transformer to the other, but it also itself is a big inductor and consumes bars. And in the case of the transformer, if you isolate it and you said, I just want to know from the transformer how much of this transformer, what is the amount of bars versus the amount of watts that the transformer consumes. No, that is transferring, that it actually consumes. The Q is much larger than the P. Much larger than the P. The Q is what we call the real losses of the transformer. And transformers nowadays are about 99.9% efficient. Meaning you put 1,000 megawatts, you get 99.9 megawatts on the other side. Only about a small fraction of that energy gets consumed by the transformer itself. Okay? So, and we'll talk about that. But the same thing goes for machines. You have a motor. Motor is a little different, but yeah, we can say that motor, or if you have a generator that is actually generates, but they still have a size, and the size of it is what we refer to as the MVA capacity. If you have a wire, same thing. If you have a wire, the wire has a capacity, and we often refer to the wire, whether it's a transmission or distribution line, well, transmission line, distribution lines, if you guys are working at Edison or PG&E or San Diego in field engineers are mostly, it's the same thing, but they're mostly concerned, they talk amps. They said, how many amps, flow through this wire? What is the capacity for that wire in terms of amperes, okay? If you go to transmission lines, the amps are still there, the voltage is still there, but the way they refer to it is, what is the MVA capacity of that line? They want to know what is the amount of the complex or apparent power that the line that you can push through the line without damaging it, okay? So there's a limit, and there's limits to how much VA you can transfer. Yes, sir.
When you say MVA, what is that for?
Oh, I'm sorry, mega.
Oh,
Oh, yeah, and by the way, some of the problems that we're gonna be doing, some of the ones that I'm giving you now, they're usually watts, bars, and volt ampere, or bars and VAs, I'm sorry. In reality, for us, the power engineers, we talk kilowatts, kilobars, and kVA. And that's mostly for industrial, commercial power systems. Distribution also, like the distribution engineers use Ks, kilos. For transmission people, they use M because they're large amount of energy, right? You're talking about MVA, megawatts, megabars, and megavolt amperes. Yeah, sorry. Okay, so that's basically what the real, imaginary, and complex apparent power is telling you about your system. Whether it is, once again, whether it's the equipment that you're sizing, whether it's the cables that you're sizing, whether the generator that you're sizing, or it's the motor that you're sizing, whether it's the load overall that you're sizing or you're analyzing. Any questions? Okay, so with that, did I forget that page too? No. There's another measurement, I'm going to say measurement, or value, as you may say, that tells you or describe the type of system that you're dealing with. And that's what we call power factor. What is power factor? Well, I don't know why, but if you go read most books, it tells you what is power factor is the cosine of theta. Well, yeah, that's the mathematical definition of it. But what is it? And I'm telling you, I see this in books all the time. The definition of power factor, the definition of power factor is cosine theta. Yeah, but what does that mean? So,
is it how much your apparent power is real?
the power factor is basically telling you what is the ratio of real and reactive power to MVA. That's kind of what it's telling you, the power factor. So the power factor definition, book definition, cosine power factor is the cosine of theta, or your phase angle. The power factor is defining the source or load ratio. And we'll talk about this in more detail. So power factor, the formula for it is equal to the cosine of theta. Whatever value it gives you, that is the power factor. Furthermore, is also you can defining the source or the load ratio, meaning the power factor tells you what the source is supplying or the ratios of real reactive and apparent power and what the load is absorbing ratios of real reactive and apparent power. Okay, power factor may be leading, this is very important, or lagging. What does that mean? Power factor by itself, whatever value you come out of here, number, it's not telling me anything until you tell me whether it's leading or lagging. Okay? So if you say, oh, the power factor is 0.8, 0.8 what? Is it 0.8 leading or 0.8 lagging? If you don't tell me, then you're not giving me the full information. And I want you to take a guess. If I say the power factor is leading, I have a box right here, and I said power factor of this load is leading. What kind of load do you think you might have in there? Say again?
Capacitive.
Capacitive load. It matches the voltage and current leading and lagging definition. So if the power factor is leading, that means that the circuit is capacitive, resistive capacitive, and is providing bars to the system. We'll talk about that in a minute. I just told you there's Q and there's plus and minus Q, but I said it goes back and forth. I'll come back to it. Now, if I tell you that the power factor is leading, of course, by deduction, you're going to tell me, okay, then it's an inductor. So I have an inductive load. But if you don't tell me, I don't know. So on the exam, don't lose those 2 points. When I ask you, solve this problem, give me the real power, imaginary power, and apparent power, draw the power triangle, give me the power factor. And if you do not tell me, you just give me the number, but you don't tell me whether it's leading or lagging, it's a couple of points off. Because you have to tell. For us, in electrical engineers, that has a meaning. The reason I'm telling you this is because I remember one time I was in the office and one of the engineers, two of the engineers in my office were in a conference call and I hear like some people yelling and I go, man, their guys are fighting. So I go in the room and I go, oh, so they're in a conference call. And I walk in the room and there's two of the engineers and they're talking to a guy who was developing a graphical user interface for one of the projects at Edison. And I just sat there. I mean, I heard there was a lot of discussion and the engineer said, you don't get it. This I'm not going to approve this. And the guy was, no, but it's right. The number is right. And he said, no, man, I told you guys that you got to give me the display and it has to have the value, but you also have to tell me leading or lagging. And the guy on the other side kept on saying, well, it doesn't matter. The number is right. So they had this argument. And by the way, the engineer that was working, he's not a very patient guy. It's a really good friend of mine, by the way. I went to school with him, but not very patient. And he just lost it with the guy. He said, you know what, man, I'm going to hang up the phone and I am not approving this project until you figure out how you put somewhere in that display that says leading or lagging. The guy who's programming it is, and he's just a programmer, right? He's programming a display. He doesn't know the concept. And the guy's like, no, because of course, if you don't say it's leading or lagging, you don't know what kind of, and it makes a big difference whether it's leading or lagging. We'll talk about that. So that is very important when power factor is leading or lagging. Power factor, the perfect one is cosine. What's the cosine of 0, everybody?
1.
1 is what we call unity power factor. Oh, that is the perfect power factor. let's go back to voltage and current and real power for a second. So if I say that the phase angle, the angle between the voltage and the current is zero, what kind of load I'm dealing with?
Resistive load,
Resistive load. What kind of power am I dealing with?
real power.
Real power, right? Oh, that's what I want. That's what the utility wants you to consume. Because that's what really what you're paying for, quote unquote paying for. We'll come back to this paying for. All right, so that is a perfect power factor. We would love every single load in the system to be a unique power factor. The reality is there's no such a thing. The power factor can be 1 all the way down to or close to 0. I'm not going to say 0, but close to 0. There's no such a thing as 0. So the maximum value that you can get out of it for a power factor is unity power factor. That means that the load is 100% resistive, and the only thing you're consuming is real power. If the power factor decreases, that means that the ratio of real to imaginary power decreases as well. Meaning there is more. The lower the power factor, lagging, not leading, lagging is telling you that that load is consuming more bars than watts. Okay? As you get closer to 1, that tells you that the load is consuming, or the source is producing more real power than reactive power. Okay, so that's what the power factor does for you. It tells you, it gives you some sense of what is going on with your load or your source. Let's see. I already did this. Okay, let me give you a couple of other. Okay, so that's power factor. Everybody okay with it? It's not just the cosine of the angle between the voltage and the current. It is also telling you what the load or the source ratio of real reactive power, real and imaginary power is. So that's the power factor, and we'll do a couple of examples. One last thing about the power factor. As I said, unity power factor, that's perfect. From the utility standpoint, if you are a residential consumer, back to power factor, lagging, by the way, we'll talk about meaning when we do exercises. From the utility standpoint, utilities classify their customers basically in 3 categories: residential, commercial, and industrial. That's pretty much how they classify them. And obviously, the industrial and commercials consume a lot more energy, real and reactive, than the residentials, because residentials are just homes, right? The load is pretty small in comparison. So, bad power factor, and we'll talk about good and bad power factor, for residential loads of customers is meaningless, because the only thing you get charged for as a resident at your house is the real power that you consume. When you look at your bill, go look at your bill. I challenge you to go look at it. Open it up, and it tells you the amount of kilowatt hour that you were consuming. It doesn't say bar hours. It doesn't say MVA hours. It says kilowatt hour. The more you consume, the more you pay. You know that, right? And I told you already that you do not. The utility is not making money on that. It's a pass-through cost. Somebody else is making the money. So don't you tell anyone that the utilities are not nice. You're using their wires to get bars so that the motor loads at your home can work. But they're not charging you for it. They're giving it to you for free. I mean it. You're still using the wire. You're not using it. It's going, you borrow it, then you give it back. But you still need a highway for the energy to flow, right? You're still using my infrastructure. So commercials do not. There's been discussions. I don't know if they're ever gonna I don't know that it'll get there, but there's been discussions among, the industry because we have the ability now to measure real reactive and apparent power very easily, which was not before. So, but there's been discussions that maybe at some point the consumers, like residential consumers, might have to start paying for some of it. But just discussions. I don't think has gone anywhere. Now, so industrial customers, we go commercial and industrial C&I customers do pay for the reactive power that they consume, but not all of it. I think, if I'm not mistaken, most utilities will begin charging giving money once power factor goes below 0.89. Okay, so industrial and commercial, and there is actually no definition in industrial commercial, but in addition to that, there is a amount of VA at which they will start considering you for to penalize you for it. So if you have power factor that is less than 0.8, meaning you're consuming more bars than what they want you to, then they will start applying charges to it. So in the case of these customers, their goal is to improve the power factor. And we'll talk about improving power factor. Right? So residentials, you don't pay for it. The only thing you pay is the watts, the real power. Bars, free. Yes.
So for industrial, they have big induction mode.
Say that again.
For industrial, let's say they have a big induction mode.
Right.
And there will be a lot of lag.
Yes.
And one way to do it is to just add capacitors to counteract it.
Correct. So we'll talk about that. How do we size them, and how do we determine the size of the capacitor based on improving it, right? And the answer to your question is right, because a lot of the commercial and industrial have a very heavy inductive loads, induction machines, lots of induction machines. So therefore, they're consuming a lot. Their power factor is very poor, right? For the most part. So, but you do. But again, that's really what the power factor is telling utilities. It's basically telling them, or the producer, or the source, is telling it at what point my system is starting to make sense so that I need to charge my customers. All right, so that's the now. Last but not least, and then I'll give you some formula, is what we call the power triangle. Power triangle. Power triangle is a very common thing in power systems. Power triangle is P is your real part, or watts. That's a measurement along the x-axis. Q, JQ, in bars is your the projection of the apparent power along the y-axis, and S magnitude is in volt amperes. So, and then this angle between the real power and the apparent power magnitude is theta, which is the angle between the voltage and current, right? So they kind of repeat. That's the power triangle. So you can have loads, we'll do this numerically. you can have a circuit or a system feeding, say, 3 loads. Okay? This is the utility. Okay? You can have a purely resistive load, so it consumes P. I'm gonna call this load 1. Load 2, I can have a resistive inductive load, so it has P, resistive in watts, and it has Q, JQ, bars. And then I can have a capacitive load. I'm gonna say resistive capacitive, so it has P minus JQ. Okay, so again, this is in watts, and this is in bars. Okay, and using the power triangle, you can actually define it, right? You can say, okay, well, the power triangle for load number 1 that is purely resistive, there's no triangle because P and S are the same, right? What is the angle between the voltage and the current for the purely resistive? 0, right? So there's no angle. There's P, but there's no Q. Okay. For this load right here, there is P and there's JQ. So you have a power triangle. I'm gonna do this. P equal to S magnitude. But this one you have P and you have Q. And then you also have S. And S magnitude is not the same as the real power. Okay? So that's the power triangle for your resistive inductive load. For your resistive capacitive load, it looks like this. P doesn't change. P is always going to be the same, but then Q in this case is negative, minus JQ. So this is P, and this is S magnitude, and this is the angle between the voltage and the current.
Yes, sir.
Yes, sir.
Could you repeat that last part one more time? So you said
The last one?
Yeah, inductive load?
This is let me put it here. This is a resistive inductive load. This is a resistive capacitive load. Okay? So the resistive capacitive load, once again, the resistor consumes real power, doesn't change, only one direction, but the capacitor is negative, is producing reactive power when we make that negative. So the triangle is, the Q is, or the imaginary part on the negative side. We'll talk about this in more detail. So, if I want to know what is the total power being consumed by these loads or produced by the source, is the addition of these 3 triangles. But the addition of P1, I'm going to say P1, P2, and P3. So what is the total power consumed by these 3 loads? P1 plus P2 plus P3. What is the imaginary power consumed by this load? 0, Q2, and Q3. That's the total reactive power seen by the source. And then last but not least is your parent source. Well, your parent source, you cannot take the magnitudes S1, S2, and S3 and add them together because remember that the real power is here, you can add them along the real axis. The imaginary power, you can add them along the y-axis. But the apparent power depends on the angle.
So it depends on the length of your P and Q.
Right, the length of P and Q, but what I'm trying to say is there's 2 components. There is a magnitude and there is a direction. So I cannot say S1 plus S2 plus S3 equal S total. No. I will do it as an example. What I'm trying to say is, if they ever ask you what is the total real power consumed by this customer or this load, you can add P1, P2, P3, assuming that you have 3 loads. What is the total imaginary power consumed by this load? You can add Q1, Q2, and Q3. But you cannot say, I'm going to take S1, S2, and S3 magnitudes and add them together, and that's the total, because you can, right? Remember, the triangles look like this. Here's S1, it has theta 1. I'm going to say that there's some real power there. there is S2, and this is, I'm gonna say angle 10 degrees. I'm gonna say angle 5 degrees, P, Q, P, Q. Yeah, I can have this too. I can have this too, but I cannot add this too because they have different, they don't necessarily have the same angle. They can have a different one, right? So I can take, the way to do it is you can take this at 10 degrees, right? Everybody with me so far? P-1? I need the complex number. And this is 5 degrees. Now the resultant of that
It's a vector
is the
addition.
total power. It's like a vector, right?
Is it easier to just add P1, P2, P3, and then add Q1, Q2, Q3, and then find the S?
It doesn't matter. Whatever is easier for you. You have homo problems, test problems. You might say, I'm just going to take PQ in rectangular form, convert that into a polar form, and that gives me the S. We'll do an example. So it doesn't really matter at the end. What the point I'm trying to make is that when you're adding, using the power triangle to determine what the total consumption of this load is, you can add the magnitudes of the, or you can add the values of the real values and the imaginary values and come up with the total. But you cannot take the complex power magnitude and say S1 magnitude plus S2 magnitude, and that's my, no, I don't know what the, I don't know what the direction is. Do I make sense, everybody?
Yeah.
Okay, and we'll do a couple of examples. Yes, ma'am?
Sorry, it's just for the inductive load, doesn't you go up?
Say that again?
So like P3 is for the inductive load, right? But doesn't it go up?
It's for a capacitor.
P3.
It's capacitor.
Oh, no, what I'm saying is, I'm just assuming that there is a load up there in my network, on my system, that is capacitive. And we'll talk about this, because there's such a thing. We'll talk about this. The load really, most likely, the load is gonna be this, the real and the inductive, resistive inductive load. This right here has a whole different function, I'm gonna say. And we'll talk about that. But the point I'm trying to make is, when do you need the power triangle? So how do you use it? Basically, you want to determine the power triangle of each load that you have so that you can then determine what the total load or combination of total load is. We'll do an example of that. All right. Any questions? So that's the power triangle. It's just plotting the real reactive and apparent power on the axis. Oh, I'm going to give you some formulas, and as we go along, there might be a few formulas that I didn't write here, and I will tell you, ooh, write this formula on your cheat sheet because you're going to need it. There is some other formulas you can use to determine, based on the information they give you. Let me say power factor again is equal to cosine theta, which is theta is equal to V minus Pi. Okay? If you want to know what the magnitude of the apparent power is, magnitude, and you know the real power and the reactive power magnitude, you can take that square plus that square root of that, it gives you the magnitude of the apparent power. So that's one way to find it. If you're looking for theta, you know P and Q, you can use this formula. Tangent inverse of Q over P. So if you know the real power, if you know the imaginary power, and you're after the angle between the voltage and the current, you can use this formula to find the angle.
Professor?
Yes,
And the quadrant doesn't matter?
the what?
The quadrant doesn't matter in this case.
I'm so sorry, the
The
what?
quadrant.
Oh, yeah, it does. But remember what I told you. If somebody's telling you something about a load, what did I say they have to tell you?
Oh, leading.
Lagging or
Leading or
lagging.
lagging, right? So that tells you where you're gonna land,
Okay.
okay? Because they have to tell you, okay? Meaning, for any load, it doesn't matter which load, they have to give you two pieces of information. They can give you the real power and the power factor, with whether it's leading or lagging. They can give you the P and Q. They can give you S and Q. You need two pieces of information to find the rest of the information, okay? I'm just giving you some extra formulas that you can use. Power factor, you can also use this formula to find the power factor, which is again the cosine of theta, which is also equal to P magnitude over S magnitude. Or you can say P magnitude divided by P squared plus Q squared. Let me see, do I have another one? Nope. There's a couple of more. When we're doing the homework, examples on the board, they will come up. What I will do is these formulas that you see here, I will put them on the cheat sheet. I'm okay with that. And if you want to make sure that you write a note on there, when I write my answer, I gotta say leading or lagging. Any formula I'm okay for you to write it. You guys already know, this is not news for you. I'm really bad at memorizing. Like, I'm horrible. Somebody, I think I know a poem, that's it. Because I maybe memorized one. Oh, the national anthem. Both my country and my adoptive country. But I'm not good at memorizing. I'm bad. You don't have to memorize. Write them down. By the way, when you go to work, take it with you. Take it with you, unless you have a photographic memory. That's the other thing I was going to tell you. The cheat sheets that I ask you to write, do the Cliff Notes still exist? You know, when I say Cliff Notes, you know what that means? Those are your Cliff Notes. When you go, trust me, there will be a time when you'll be sitting on your desk and somebody says, hey, what is the equation for real, reactive, and apparent power? You have your cheat sheet. You have it handy. There it is, the exam. I just watched a show this somebody recommended to me last night. I was falling asleep, but I was fighting it, but I watched it. The show is about, has anybody ever heard of the company Qualcomm? Qualcomm, down in San Diego. Andrew Viterbi, the guy from USC. Right, they're the ones who invented, I don't know, one of the algorithms for CDM something, I forget, is the cell phone, right? The show was about Qualcomm looking for electrical engineers and computer scientists. They were growing, they were looking for, and they hire engineers, and they were having a really hard time because the engineers, they can do just about any equation. But they had a really hard time connecting things, putting things together, because the School of Engineering were not training them on that. The other thing that a lot of the people that they hired had a really hard time with failure. And I kind of get it. Like, if you, please, I'm not telling you not to be a 4.0, be a 4.0 student. But sometimes you spend so much time focused on that there's other skills as an engineer that you need. And one of them is visualizing things. Like, they don't visualize things. The other thing is they cannot put things together. The third thing, they cannot explain what they're doing. They can be the brightest people. So the company decided to open the school in San Diego. And there's been a lot of debate. And the person who sent me this video is actually is a teacher. Is my daughter's boyfriend's mom. I said, I want you, he's an engineer, I want you to watch this. And at some point she told me, I want you to share this with your students because you're the engineer. I said, yeah, and I'm watching and I'm thinking, yes, that's exactly what happens when companies hire engineers. There's so many other skills, including the ability to fail. Because if you're a 4.0 student, you do not know what failure means. I really, I'm going to bring it to you guys and the name so you guys can watch it and think about it.
Let me guess, you forget the name already?
No, how do students succeed? How do people succeed? That's the name of the documentary. And it is really good, but the thing I was gonna tell you guys is this, that I told this person, I said, Jen, you and I are gonna get together soon. We're gonna sit down and talk about this. I'll give you my five. You know how much I've been pushing for Cal Poly does, which is learning by doing. I'll give you all these formulas. You're in the lab. But I ask you, can you show that this formula works once you connect the equipment? Can you measure that? That's the piece that a lot of schools are falling behind. They're not doing it. They're not teaching the engineers how to actually get things and connect them together. So write the formulas, put them on the cheat sheet, use in an exam, take them with you the rest of your career, but do not forget what they mean. The formula is nothing without meaning. So I'm gonna leave it there. So I'm gonna leave it with this ones, and along the way, I'll put more, and every time I'll say, hey, write this formula on your cheat sheet. Any questions about real, apparent, power, reactive power, power triangle? Okay, so let's see. Now that you know that information, let's do a couple of problems. Let's see, examples. Let's see. We kind of had this one already. Kind of, sort of. We did part of it last week. All right. Example one. Or example. No, today. We say that a voltage source V of t is applied to a load consisting of 10 ohm resistor and J 3.77 ohms reactive load, both loads, resistor and did I put ohms? Yeah. Find the real P, reactive U, apparent is power factor and the power triangle for this system. So basically what we have this, we have a resistor, we have an inductor, we have V of t, and I'll define it right now. I of t, I don't know what that is. I know this is 10 ohms, and I know this is J 3.77 ohms. We did this problem last week. Well, I did this problem last week with the weekly. The voltage, V of t, instantaneous value is 141.1 cosine omega t. All right, simple. Now we know how to do this, but like I said, I already did this, but so I know that the phasor, voltage phasor, is going to be 141.1 divided by square root of 2. Angle, everybody? 0, right? There's nothing there. Or V phasor is equal to 100 volts at an angle of 0 degrees. So that's my reference. Okay, so I know the voltage and let me see. Hold on a second. Nope. I almost messed it up. They're parallel. Sorry about that. J 3.77. We did that last time, right? We know, if I know the voltage phasor across these loads, I can find the currents, right? And we did that. I'm gonna do it again, but we already have it. You already have it. So I know that the IR, I'm gonna define this as I resistive current, IL, or X, I'm gonna call it X for reactive. Phasor, so IR, we said that was 100 volts, angle 0 degrees divided by 10 ohms, right? And then we came up with the value for that, IR was equal to 10 angle 0 amps, volts, I'm sorry. So that phasor, first phasor. The second one is the current, the current flowing through the inductor, Ix is equal to 100 volts, same voltage across the inductor, 0, J 3.77, and then for that we came up with the following. This is in volts, this is in ohms. Ix we said was 26.53 angle of minus 90 degrees. That makes sense, right? The current is lagging the voltage because we're feeding a pure inductor. So, all right, so we're good. And this is an amp. Oh, by the way, I uploaded slides with these problems. They're not as nice. I need to clean my slides. There's somewhere I made a mistake, and I think I corrected it. But it's a very, very minor mistake. I defined this at 26.53. I'm sorry, see, I made the mistake. 35. That, if you do this, this is what you come up with. But then when I start working on the problem, on the slides, somehow I switch these two values. Okay, so if you see it again, my apologies. The actual answer is 26.35, a minus 9. And I got some numbers here, which when you plug it into your calculator, you lose some accuracy, but it's very minor. And I'll tell you what I'm talking about as we go along. Anyway, so I have now the current flowing through this guy, and the current flowing through this right here. The phase angle, theta, is equal to phi v minus phi I. So in our case, that is the voltage. Let me see, did I do both? Oh no, I'm sorry. See, what I need now is the total current. So how do I get the total current, everybody? How do I get the current flowing? Not the IT, but I of the source. I'm gonna call S.
Adding.
Just adding these two phasors, right? And we did the last time. So I'm gonna call that I total. So I'm just gonna put a T right here. It's equal to IR phasor plus IX phasor. And that was 10 angle 0 amps plus 26.35 angle of minus 90 degrees amps. And then I had an I total with this that we came up last time was 28.35 angle of minus 69.34 degrees. Did I do this in MATLAB, by the way? Or no? You guys remember if I did it on MATLAB?
I think you didn't simulate.
I did on Simulink, right? Yeah. And that's the ones that I told I was going to give you, and I haven't uploaded it, but I will. Anyway, so this is now what's being, I'm going to call this the electric utility. This is what the utility is feeding. But I need to know now in terms of, not so much in terms of current, but I need to know in terms of power. How much real, because there's an R, how much reactive power, because there's an L, is this customer asking me to provide. All right, well, we use our formulas. Let's start by the angle O. Yes, that's what I was going to say. I almost made the mistake. I start going this way. I start looking at these angles. Forget about those angles. The angle that you're interested in is in the angle of the total, not the individual for now. We could use it, but let's do it this way. You can do it both ways. All right, so that's the angle that I'm interested in. So what is the angle between the voltage and the total and the total current? So theta is equal to phi v minus phi I, theta is equal to 0, right? That's the voltage at 0 degrees minus 69.34 degrees. That gives me theta equals to 69.34 degrees. Everybody okay with me? And I
Yeah.
made a mistake anyway. I think I double checked, but. All right, so I know the angle. Ooh, that's great. I know the current magnitude. I know the voltage magnitude. I have enough information now. So I'm going to say that P is equal to V magnitude times I, not phasor, times I magnitude cosine theta. And this is in watts. That's my formula. So P is equal to 100 volts times, what was it, 28.35? This is where I made the mistake. If you see my slides, I think I corrected, but if in the slides that I'm gonna upload, you see, I might have left 28.53. I'm sorry. If I didn't do it everywhere, just make sure that you corrected it. A cosine of 69.34. This gives me approximately, depending on your calculator, sometimes depending on how many figures you're keeping, but I get to about 1,000 watts. Oh, so with a 100 volts feeding a resistor of, I'm sorry, with 100 volts magnitude feeding a resistor of 10 ohms, I'm consuming about 1,000 watts, okay? What about the second part, which is the next thing, which is the imaginary power? I know the voltage magnitude, I know the current magnitude, and I know the angle. So the formula for that is JQ is equal to J V magnitude again, I magnitude, sine of theta. This is in bars. Okay, so JQ is equal to J 100 times 28.35 sine of 69.34 degrees. And again, this is in bars. Okay, and JQ then is equal to J 2656, approximately 2656 bars, volt amperes reactive bars. Okay, I want you to look at, so again, here's the circuit, right? A resistive and an inductive load. And that's the amount of real power that is consuming, and that's the reactive power consuming. Let me ask you, I want you to look at the magnitude of the real power and compare it, just a quick comparison, magnitude-wise, with the apparent power, with the imaginary power. What can you tell me? If you're comparing those two magnitudes, 1,000 versus what? 2,656. You're telling me that this is almost 2.5. This circuit, whatever this load is consuming almost double, 2.5 more than the resistive part. Do you agree with me?
Mhm.
Do you agree with me? Okay, what did I say?
But it's not consuming any power.
Let's say consuming for now.
Okay.
We'll get back to that definition. Let's say it is consuming. Let's say flowing through your network. Well, this load is asking you, wait, is this what you think the utility wants? What is that the utility wants? What would they be like so happy with the customers if they consume
More real power.
real power? But this load is asking for more reactive power than real power. That's not a good thing. That's not a good thing. And just by looking at it, you don't even have to go any further. Just by looking at it, you can say, I know this is not good. This load is bad. And say, for instance, this is in kilo omega. That means that, oh my God,
Yeah.
whoever is doing that is just sucking a lot of watts from my system, from the source. So now those magnitudes at least are giving you some hint. Do you believe this will have a really good or really bad power factor? Or okay power factor? What are your thoughts?
Mm.
Well, it's not gonna be so good. That's it's not pointing in the right direction. It is looking a little bad. But let's see how bad. Okay. So where's my black? Okay. So, but before we do that, let's. I'm sorry, I didn't mean to do that. Before we do that, we have the real power, we have the imaginary power. Let's compute the apparent power. There's two ways of doing it. You can say S is equal to P plus JQ in volt amperes. So S is equal to 1,000 plus J 2656, and the whole thing combined is volt amperes, right? And this is in watts, of course, and this is in bars. Okay? All right. That's simple. If I'm asking you on the test, hey, can you give me the real, imaginary, or reactive power and apparent power? You write that? You're good. That's it. That's the answer. Now, there's another way to do it. You can also do this. Is equal to V phasor times I phasor conjugate. So S is equal to 100 angle 0 times 28.35 angle of 69.34 degrees. Yeah, because remember, the angle of the current was what? Was negative, right?
Negative.
Because it was lagging. But if I take the conjugate, that then automatically becomes
Positive.
positive. So if you multiply these two values, you get, let me see, you get the same thing. I'm gonna write it, you can write it in polar form if you want. I'm just gonna write it in rectangular form. I did it on my calculator and thus J2656. I get the same thing. This is in volt amperes, right? Again, watts, bars. So you were asking me, right? Like it doesn't matter. And if you know that sometimes they don't provide you with the voltage, they provide you with the current. You need to know the voltage because I can use. I'm sorry. Let me take the back. Sorry. If they provide you with the phasor voltage and current, both, you can use this formula and come up with the apparent power, right? And automatically you just got the real and reactive, the real and the imaginary reactive power, right?
Mhm.
You see how you can approach it different ways, and it doesn't really matter how you get there. All right, so then they said draw the power triangle, and also the power triangle is going to give you some sort of hint. One, if I kind of do it to scale, 2.5. So P is equal to 1,000 watts. JQ is equal to J2656. 2656. And again, this is in bars. And this my S magnitude is, by the way, this is how I got S magnitude is equal to P squared plus Q squared. S magnitude is equal to the square root of 1,000 squared plus 2656 squared And that gave me 2835. 2835 magnitude. And this is in volts amperes. So this is magnitude is equal to 2835 volts amperes. What is this angle, everybody?
60.
69.53.
34.
Was it by 3 or?
34.
69.34. Oh, okay, here's my power triangle. Now, looking at the power triangle, assuming that you somehow put a little time to try to get it close to scale, look at the imaginary magnitude compared to, I mean, the real magnitude compared to the imaginary. Man, big difference. You see that? A good power triangle will be like this. Where your Q is really small and your P is really large.
A good one is there's no triangle.
It is not real, that's not.
The good one is there's no triangle.
But,
That's right.
But,
The perfect world will be if there is no triangle and you just have a S and P be equal to each other, right? But there's no such
but that's
thing.
not real.
That doesn't exist, everybody. Okay? So, with that, I know the power triangle. What is the last thing that I want? Oh, what about the power factor? Power factor is equal to the cosine of theta, which is equal to the cosine of 69.34, and that is equal to, I'm going to put it here, power factor equals 0.353 lagging, because it is an inductive load. Is that a good power factor?
No.
That is actually a very poor power factor. Which is, that is why.
You're supposed to leave early.
Couple more.
You gotta get rid of it.
I check and it says it takes 2 hours to get, 2 hours and a half to get to Visalia, but I'm okay. I go to bed late anyways. All right, so any questions? Everything good? I have another problem that I was gonna do. Let me see. No, this is the next one. Okay, before I continue, how many homeworks have I put in there? Two, right? With what we have covered so far, can you solve those now? Yes, right? I think you could.
Definitely.
I think you could. Have I created the drop boxes?
For one.
For one. Okay, I'm gonna create the other drop boxes. So I'm gonna put more homework. So more homework. Before I get to the next thing, I was gonna say this. I think I need one more lecture after this. Lecture maybe and a half. And we'll be done with the fundamentals, which means that we will be ready for the first exam. Don't panic. I'm not saying we're going to have it right away. All I'm saying is I want you to start thinking about that. So the reason I'm going to put more homework is because I want you to start practicing this, okay? And then start uploading the homeworks. I don't check, like I said, I don't check every problem. I just check if you turn it in. The other thing that I check, I would really appreciate it, especially when I'm traveling, it's perfect time for me because I get on the plane, I just pay whatever money for the internet, and then I check stuff for you guys. I don't tell my boss. That's what I'm doing on the plane. I'm checking homeworks, I'm checking stuff. So if you can, I'm going to open the other Dropbox, and if you can upload it, I'll appreciate it. But don't feel super obligated. I just want to know whether we're okay with these concepts or not. All right, so the next question is, oh, that's a really, really poor power factor. And how do engineers fix the problem? What will you do? Like, okay, if they're charging me, say this is a factory, and that factory is at certain time of the day, I don't know, because the power factor changes, by the way, throughout the day. Load changes. But some period of day when they're at maximum capacity, they have 0.3 power factor and the utility is going to hammer them. They're going to be like, oh, wait, we're going to charge you. And I don't know, honestly, I don't know if you work for Edison, PG&E, or San Diego. You can go you can go ask somebody in field engineering or customer service, whatever. Hey, how much do we charge for bars for these customers? And they'll tell you, but I don't know. But how do we fix the problem? I gave you some pictures on the slides. And we're going to talk about both ways. Hold on. I'm not going to put the slides, but I want you to take a look at them one. And if you can look at them there, that's good too, but I just want to refer about them. Give me 1 second. Oh my God, I thought I had them. And I uploaded that on your on Canvas. Let me see, React. I took that lecture React PowerPoint presentation. And I'm gonna talk about this stuff. I gave you some pictures of how customers and utilities, what do they do to improve power factor? First of all is, how do I provide bars close to where the demand is so that the utility doesn't have to send them? There's two ways. One way is by using capacitors, capacitor banks. I gave you some picture of capacitor banks. The first one that you'll see on the slide is a substation capacitor bank. Why substation? Why would the substation have capacitor banks? Substation, the main component, like the main purpose of substation is power transformation from one voltage to another. What do you use to step up and step down voltages? Transformers. You can have thousands of things hanging into that substation, but the core of the substation is the transformation. It's the transformers. And transformers consume a lot of bars.
Those are inductive, right?
Right, because they're big inductors. So that's why you put capacitors inside the substation to improve the power factor of the substation. Basically, what you're doing is you're providing the bars that the transformer needs so that it doesn't come from the generators of the sources, right? That's why, there's a lot of and we'll talk about the sizes and all that, but that's why you have. So I give you a picture of a typical capacitor bank at a substation. The other one is, and this one they both have, but this one has dual purpose. Distribution capacitors, and you see this on the pole. You see these cans, they look like, like boxes that on the poles. That's a capacitor bank. And what the capacitor bank with the distribution circuits do two things. One of them, they improve the power factor. Basically, what they're trying to do is trying to get bars closer to the customer, right? Number two, they improve voltage. Capacitors have the ability to raise the voltage. As you turn on bars, the voltage will start going up. The reactors have the opposite effect. They reduce the voltage. So most loads are reactors, so they reduce the voltage. So it helps your voltage profile. And then last but not least, you can use synchronous machines. It can be a generator or a motor. And they can help you improve the power factor. So the asynchronous machine have the ability to inject, meaning be a capacitor, or absorb bars, meaning an inductor. Capacitor is just a capacitor, right? That's it. The synchronous machine, and when we study synchronous machine, we're going to talk about that. Depending on how you manage the field, you can make the machine act as a capacitor or act as an inductor. They can do both. So you might say, out of these three things, if I have one that does both, what happens if I need bars? If I need to get bars out of the system, I can use the synchronous machine. Yeah, you can use the synchronous machine. Can I use the capacitor? No, you can only inject. So you might say, then why in the heck am I going to use capacitors? Why don't I use synchronous machines? They're more flexible. I can do more things with it. very expensive. Very expensive. Those are very expensive bars. Capacitors are cheap in comparison, right? But there is a lot of good things about synchronous machines. Let me just say this. One of the challenges, especially when you're trying to improve power factor, one of the challenges that you have from capacitor banks is that when you have disturbance and the voltage comes down, the amount of bars, if you have a capacitor bank that is rated for 100 bars, that is 100 bars at nominal voltage, when the voltage is perfect. As the voltage goes down, the bars go down. As the voltage goes up, the bars go up. So it is a function of the voltage. Okay, like this. I'm going to go again. I'm going to say this is capacitor. This is Q minus, just a capacitor. Here's voltage. This is 1 per unit voltage or rated voltage. It's like this. As the voltage comes down, the amount of bars you get out of the capacitor reduces linearly. So that's one challenge with capacitor banks. Okay, and we'll, like I said, we'll do this later in MATLAB so that you guys can get an idea. So that's one of the problems. And when do you need bars? Basically, you need bars when the voltage is going down. So, okay. What about synchronous machines or synchronous motors or generators? If you look at they look like this. They're more like this. Here's the voltage. Here's plus, I'm sorry. I should have drawn that on the other side. It's minus Q plus Q. Okay? So it can be a capacitor, this synchronous machine, and it can be an inductor. Okay? And by the way, it gives you this much bars, whatever is rated for, in either side, either injects or absorbs. And as the voltage goes down, it doesn't really all the way down collapses until it gets to like at a very low voltage, then it starts collapsing. So the synchronous machine, the beauty of them is that they can handle they can handle voltage much better than capacitors. They don't collapse right away. I had a boss one time. He told me, he said to me, capacitors are like cats. And synchronous machines, he told me, synchronous machines are like dogs. Okay, Bharat, say that again. Capacitor banks, I want you to remember this. Capacitor banks are like cats. And synchronous machines are like dogs. Okay? When you need them the most, cats are not there for you. If there's a fire, the cat will run and say, see you, sucker, I'm gone. I'm going to save my life. So when the voltage is going down, the capacitor says, see you later. It starts collapsing, no much bars out of it. The synchronous machine is a dog because if there is a fire, the dog makes sure that you get out of the house safe before the dog gets out. They're very loyal. A synchronous machine, they're very loyal. The voltage is creeping down. The voltage is coming down. They keep on pushing bars. They keep on pushing bars. They keep on trying to help you with the voltage and the power factor. Okay? But as he said, the challenge is that they're very expensive. I'm going to give you the number. I keep on saying I'm going to find the number. I'm going to give you the ratio of bars. How much do you pay for dollar per bar on a capacitor versus dollar per bar on a synchronous machine? And I can tell you it's a lot. So I gave you some pictures, and we're going to talk about both of those. But capacitors, that is what we call power factor correction or reactive power compensation. That's the right term for it.
Professor,
Yes.
are you saying synchronous machines can create both?
Can what?
Synchronous machines can create both positive and negative reactive
Right.
power?
Right. And we're gonna get into the theory of that. How you do it is the synchronous machine has an external source. Synchronous machine has two sources. Has the three phases from the utility, A, B, C, but in addition to that, it has a DC source. And how you adjust the DC source, and basically what you're doing is how you adjust your DC source is how you change the behavior of the synchronous machine. And as I said, we're gonna talk in more detail, but I'm gonna give you some preview. The way you can think of a synchronous machine is, this is the rotor, here's the shaft, is going around. There's a DC source, and I want you to think about this. I'm going to talk about, like I said, more detail, but for now I want you to think about this. The rotor of a synchronous machine is an electromagnet. It's not a permanent magnet. This rotor becomes a north and south magnet not until you apply a source to it. Okay? So, as this is going around, you're developing, there's a field. It's a magnetic field. So the magnet, just like Earth, right? As I increase and decrease the DC source, if I adjust it, I can make the machine what we call over or under excitation. And that makes the machine be either a capacitor or an inductor. So it's a function of the DC source that I'm applying to the rotor, we call it the excitation of the system. That's what determines the amount of bars you're getting in and out. And you can do it very precisely. You can say, oh, I want the bars, they can increase linearly, meaning like this. They can go up like this as a line. On the capacitor, there's steps because you're turning capacitors as steps, right?
Does that rotor rotate like this or?
Both. It depends. If it's a if it's a hydro generator, it rotates like this. If it's a steam generator, it rotates like this. Now, you can have a machine, a synchronous machine, that is neither a motor or generator, it's just rotating to produce bars. You do not need, and there's a name for those. The one that I showed you on the slide is what we call a synchronous condenser. Basically what it is an induction machine with no load. The only purpose is not to produce, it's not to consume real power. The only purpose is either to produce or to absorb bars. to improve your power factor, to improve voltage. That's the only purpose of it. And the name of it is synchronous condensers. Utilities got rid of a lot of synchronous condensers because the expense, because of the maintenance. Capacitor, you put it in there, a fuse blows, you go replace the fuse. A can blows, you replace the can. A machine, you have to go and do maintenance on it every year. You gotta lubricate it, you gotta clean it, there's a lot of stuff that goes, so very expensive. But utilities are starting to get back into the business of using synchronous machines to improve power factor. And voltage stability is another thing. There's one done in, the latest one, at least in Southern California, is done in Irvine. It's called Santiago. It's a ginormous motor. It's about the size of this room. That's the only thing it does. But again, they're not cheap. Now, let me say this: if you can use machines like synchronous motors to improve power factor, and you have a factory and you want to drive a load with that, you want a motor to drive a load, wouldn't you say, by the way, induction machines are bad? Wouldn't you say, oh boy, if I can use the machine to do the work, the peak, But in addition to that, I can use the byproduct, which is Q. Oh, I'm doing two things. So a lot of industrial customers, especially in refineries, as an example, or factories, use synchronous motors because they use them to do the real power, the real work, to drive something, a fan, a pump, whatever. And in addition to it, they can get bars. They just happen to be more expensive. We'll talk about that. But those are the two ways. I give picture. If you have any more questions about it, let me know. Ideally, I said this already. Ideally, systems, and I'm gonna say AC systems, by the way, not DC. Will deliver P, real power, only. But that's ideal. There's no such a thing on an AC network. And I said, but systems are not ideal. And reactive power is necessary to generate a magnetic field, magnetic field. And we'll talk about it in more details. So what consumes, is consumed with two M's, everybody?
No.
No, one, right? Consume, say it like that. But what consumes reactive power? Question mark, power. Well, lines on your system, transmission and distribution, transformers, induction machines or motors, machines. Let me see. I don't know. Loads, of course. Okay, just put a few. So what consumes red lines? They require reactive power. There's a magnetic field, right? That you develop when current is flowing. You're getting a magnetic and an electric field. So there's an inductance there. Transformers, they're big coils, so they're big inductors. Induction machines, yeah, both stator and the rotor have copper windings, so therefore bars, L, and loads, right, in general.
How do you define consume and produce?
Say that again?
How do you define consume and produce reactive power?
Yes, okay. So let me say this. Do I have, actually I have them here. I have a system here. So I'm gonna draw a system, and this system has a line with that, and the line has resistance and inductance, and then transformers. You find a transformer right here, and this transformer you can represent it as a resistor and inductor. As a matter of fact, you can just leave the inductor if you want, and then you have loads, and the loads have resistance and reactance. Okay. So the resistors, of course, these guys are the ones that consume P, and P. And the reactances on your line and your transformers are the ones that are consuming Q. Okay? your line hopefully will have very, very small P and Q in comparison to the load. There's a lot of work that goes into minimizing the amount of bars and watts or the amounts of real and reactive power used by the line. Very low transmission line, and I'm just gonna say this, you probably talk about it next semester when if you take power system analysis of transmission line. Long transmission lines have a lot of capacitance as well. But for now, we're gonna say it's not a long line, it's a short line. And then the transformer, of course, has a lot of reactance. So, but hopefully you're gonna minimize. This is the bulk of real and reactive power being consumed by the system. So obviously you're gonna have P. We're gonna say for now it's lagging in that direction and Q in that direction right now. All right, so so we say that the idea is to provide the reactive power closer to where it is consumed. Meaning, so if I have a demand of reactive power here, here, and here, this is my Q demand that the source is having to provide. By providing the bars closer to where the sources are, or bars, or the sinks of bars, that helps me improve the power factor seen by the source. So in other words, if there is a substation, I said that, if I can put capacitor banks right here, so that I can serve, not all of it, but I mean at least some of that, Q minus Q plus Q, I'm investing. If I can put some capacitance right here, I'm in business. I'm consuming bars, but then I'm producing bars right here, minus Q. All right, so he was asking, how do you know what is consumed and what is produced on here system? This right here, QL is what we call is positive, by the way, we call sink of bars. L is a sink of bars. And remember we said this, remember I said that I'm gonna contradict myself at some point. Now I'm gonna contradict myself. Remember that I said when we were talking about power, instantaneous power, and I said Q, forget about capacitor for now. Q is taking and giving it back, taking and giving it back. So why do you say it's consumed? This is how we electrical engineers define it. We define it this way. We're going to freeze the system in such a way that the minute that we decide to freeze it or to put the system into steady state, bars are flowing into the reactor. So if I freeze the system and I said, I'm going to freeze the system, and bars at that point, when I take the snapshot, I'm not moving time. Snapshot is when total amount of bars were flowing into that inductor. What's the capacitor doing?
Taking
The opposite. Completely the opposite. So based on that idea, we can say by agreement, power engineer said by agreement, that's how we're going to analyze the system. We're going to say that we're going to freeze time and we're going to take a snapshot when the reactor is absorbing maximum reactive power. The capacitor is doing the opposite at that point, right?
Providing the bars.
Providing bars, right? So one is, I'm going to freeze it right there. They're doing this. But what I'm going to say is, to analyze the system, I'm going to say that they're doing this. So L is a sink of bars, and Q Q is a source of bars, source.
You mean C?
So this one absorbs bars, this one produces bars. Make sense, everybody? Okay, so, good with that? You good with that?
Yeah.
Okay. Now,
Basically, it's telling me that in a capacitor, you're basically providing the inductor ability when the capacitor discharges, so the power plant don't have to do that.
correct, correct. That's exactly what I'm trying to do. Let's do this. I'm gonna go do this. I'm gonna skip a few things because I think some of them I mentioned. But so now think about this. Think about what we have and the definition that I just provided you. So what if I have the following? What if I have this? Let me go do this one right here. I'm gonna have system one. Back to this. Source. A line or cable, conductor, whatever you wanna use it as. And then I'm gonna have a load that is resistive and inductive. Then I'm gonna have a switch that is open, and I'm gonna have a capacitor right here in parallel with this. This is my load, okay? This is my load. And I have this open. I'm gonna just put some arbitrary numbers for now. I'm gonna say that this is consuming, let's focus on the bars. Let's not even talk about the real power. I'm gonna say that this is consuming J100 bars, okay? And in addition to that, there's bars going here. I'm gonna say that this line is consuming 2 bars, okay? So and again, I'm just talking about imaginary power. Forget about the real power for a second. So if that is the case, if I have a sink of bars of 100 and a sink of bars of 2, how many bars do have to come from the source? 102 bars. Come from the utility or the source or the generator or the solar PV plant, whatever is producing the energy for you.
That would be 2 to J2 bars, right?
J2, right. J and J, thank you, yes. All right, that's great. So 102. That's case number 1. Case number 2. Same line, same load. The load is not gonna change. J100 bars, J2 bars. Okay, everybody okay? And J102 bars. Somebody says to me, you know what? Close the switch. Boom. And I'm gonna tell you, this capacitor size is J minus 50 bars. Okay? Oh, I'm gonna close the switch. Great. Close the switch. Energize the capacitor. Now the capacitor is giving me J50 bars. Okay? Oh, so that means that the bars will start going and saying, hey, where's this thing? Where can I go? Goes here. So if 50, after I close the switch, I close the capacitor bank, if I'm injecting 50 bars into my system and it goes into that, now how many bars do I'm asking the utility now for?
52.
I'm asking for J52 bars. Okay? Do you see what happens? Everybody okay with that? So basically what I'm doing is if you look at this as a black box, okay, a factory, the utility before the inside your factory, before you close that switch, the utility was telling you, I'm giving you 102 bars. I don't know what the real power is, but assume that the power factor was really bad. It was like 0.3. That's that's what the utility sees. When I close this, then the utility says, ooh, my bars are gonna go down. I just need now you're asking me only for 52 instead of 102. Yes, sir.
Don't you have to keep that capacitor charged so it continues to supply those negative 50 bars?
That's a very good question.
Because it will discharge as it provides.
So remember the capacitor is doing this? Charge, discharge, charge, discharge, charge, discharge, charge, discharge,
When
charge,
it's
discharge.
discharged, the inductor.
The inductor is,
When
so
the inductor go backward, it charges
the way,
the capacitor.
yes, the way you can see it is
Yeah.
this. If you wanna play time, start playing time. They're doing this.
Oh, I see. They're handing back and forth.
Yeah.
Right.
Right? They just gave it,
And
but,
they are completely opposite face of each other. So that's what-
correct. They're completely opposite face of each other. So now, inside, in there, you're still dealing with this. This doesn't change your motor. If this is an induction machine, the motor is consuming what it's consuming. You're not gonna change the behavior of the motor. What you can do by adding the capacitor and by providing the bars that the motor needs is that you are telling the utility not to give you that. Therefore, improves your power factor. Improves the power factor what the utility sees. But the load power factor is never gonna change. Do I make sense?
But like business-wise, it depends on how much the penalty and how much the capacity.
Thank you.
Yeah.
Thank you. So and that's the next lecture. We're gonna talk about this. How do I determine the amount of bars that I need to improve the power factor for one? That's what we're gonna talk about next. Point I'm trying to make is this. The load does not change. A motor or transformer, whatever the device that you're dealing with, does what it does. Is how the utility or the source will see it. So bars, by the way, there's problems with too much bars flowing on your system because your voltages can get really horrendous if you have too much bars flowing. So you want to minimize the amount of bars. There's no such a thing as zeroing it. There's no such a thing. All you want to do is you want to get to, meaning there's no such a thing as the utility seeing you as a unity power factor. No. The only thing you can do is you can improve it. You can make it more palatable. That's what I said. Anything below 0.8 on average in the United States, I'm going to say utilities will charge you. If you improve it to 0.85, you're good. You're off the hook. You don't have, again, it's a question of economics, right? If you can say, if I can get away with making the power, if it's less than 8, but if I can make it 0.83 and the utility will forget about me, that's what I'm gonna do. The businesses will do the bare minimum, right? And we'll get to that. We'll get to how do we size it, first we gotta measure the power factor that the utility sees, then we gotta improve it by using capacitor banks. You know, I use capacitor banks. How do we determine that? How do we quantify the amount of bars? So that's what we're gonna do next. I think it's a good time to get home. Yes, sir.
When are we gonna drink?
When are you gonna drink? Anytime. If you're over 21, anytime. I tell that to my kids, if you're over 21, anytime, but I know that is not happening. I know it's not happening. I don't get full, right? I think there's no that.
Like, if you go drinking with any of us, how are you going to get home?
Say that again?
If you go drinking with